How does an ADC work in microcontroller interfacing? Imagine trying to measure the temperature of a room with a device that only understands numbers. That's where an analog-to-digital converter, or ADC, comes into play. It acts like a translator, turning real-world signals into digital data your microcontroller can understand. This process is essential for working with sensors, potentiometers, and other devices that give out analog signals. An ADC works by taking a snapshot of the voltage at a specific moment. Think of it like a camera capturing a single frame of a moving scene. This snapshot is called sampling. The ADC then divides the range of possible voltages into a set number of levels, a process called quantization. Each of these levels is assigned a unique binary number, which is the encoding step. Most microcontrollers have an ADC built right into their chips. To use it, you connect the sensor or device to one of the microcontroller's pins designated for analog input. You then configure the ADC through special registers that set things like the reference voltage, which defines the maximum voltage it can measure, and the speed of conversion. For example, if the reference voltage is 5 volts, the ADC can measure anything from 0 volts up to 5 volts. The ADC inside the microcontroller often uses a method called successive approximation. It compares the input voltage to internal reference voltages generated by an internal digital-to-analog converter. It starts with a guess, then adjusts until it finds a match, and finally outputs the corresponding digital number. This process happens very quickly, usually within a few microseconds. The resolution of the ADC tells us how many different levels it can distinguish. For example, a 10-bit ADC can produce 1020 for different digital values, ranging from 0 to 1023. Higher resolution means more precise measurements, but it also takes a little more time to complete each conversion. In real-world applications, ADCs are used to read data from sensors like thermometers, light sensors, or pressure sensors. If a temperature sensor outputs a voltage that increases with temperature, the ADC converts that voltage into a digital number. The microcontroller then uses this number to calculate the actual temperature, which can be displayed or used for control purposes. To get accurate readings, you need to set up the ADC correctly. This involves selecting the right input channel, starting the conversion process in software, and reading the digital result once the conversion is complete. Timing is important because if you read the data too early or too late, the measurement might be off. In summary, the ADC in microcontroller systems is what allows us to measure the analog signals from the real world and turn them into digital data. This capability is fundamental for many embedded systems, enabling everything from simple sensor readings to complex automation tasks.